Hello, this is Galactic Griggs. NASA is trying to pull a rabbit out of the hat once again to try to launch this month. There is an option that may give us a launch on the 21st or thereabouts of September. And there's two other options we're looking at. So there's three options going forward. I'm going to talk about that. We'll talk about the scrub, the nature of the fuels used, some of the technical difficulties, and we're going to pair a couple of other engines. And we're going to talk about SpaceX and what they're trying to do. So a lot of stuff to talk about. We'll also, like I said, talk about the nature of this scrub. So hang on, guys. Here's what it boils down to. There are three primary options that NASA is evaluating for a launch. And there's one favored, which is an attempt to do it this month without rolling back to the pad. Everybody has come to the foregone conclusion. All the other channels and information you're saying is that they got to roll back to the pad. Well, maybe not. But this all depends on the 45th Space Group, the organization from it used to be Air Force, now it's part of the Space Force that controls the Eastern Test Range launches. And you have to have their permission to fly. There's no doubt about it. And their mission is public safety. So the first option is to repair that 8-inch quick disconnect that gave them the problems with the leaks before, and to conduct tank testing about the 17th of this month. Then they would roll back for FTS battery change and other work. And then they'd roll back to the pad. And that launch option, though, because of all the work required and the change outs that they would do, would probably get us a launch about the 12th of November. So that's the longest option. They do have then about a 9-day margin, a window in which to conduct the launches. So they got some time to work with. And NASA does like margin to a degree, but that's a later date. And they would soon launch earlier if they can. The option number 2 is to roll back to the VAB, repair the quick disconnect in the VAB without doing all the prior testing in the pad, perform ambient checks, change the FTS batteries, which they'd have to do if they roll back to the VAB, and a few other things. And then they would roll back to the pad. Then launch attempt for that would be within the launch period 27, and that would have them launching on maybe about the 23rd of October. Oh yeah, that option 1 was for launch period 28. There's various launch periods that have to do with and are governed by opportunities of the position of the moon as much as anything else. All right, so that launch period, option 2, does not give any margin though. So that's a tight schedule. Now, again, launch option number 3, they would repair the 8-inch quick disconnect on the pad. So apparently they can do this. They would conduct tank testing on the 17th, which is, about 11 days from now, and obtain range FTS battery waiver. They would have to have a waiver on the batteries to make this happen. And they'd also have to have a waiver on the time for testing, a certain end-to-end testing. So this is absolutely contingent on an FTS waiver from the 45th Space Group. They got a new name now, but I still call them by the old name. That's what I'm used to calling them. So there is an FTS end-to-end abbreviated pre-flight test that occurs in the VAB prior to rollout of the pad. That's one of the major milestones. Now, in other programs, there's going to be something similar. So, all the launches are governed by the range. They have the same requirements, and this is the way that they would be implemented by NASA. So there is there's another FTS end-to-end test that's conducted, it's an abbreviated test, on the day of launch and prior to launch. So if a launch is scrubbed more than 15 days, but less than 20 days, the pad test can be redone. I mean, they can do that abbreviated test at the pad. But if the launch is beyond 20 days, they need to roll back to the VAB to conduct the end-to-end testing that has to be done there. Of course, it has to be safe first, and that end-to-end testing has to be done in the VAB. Now, under proper circumstances, the range allows for certain waivers to be passed, and NASA is applying for an extension of the waiver that they've already got in hopes of a launch on the 21st. Now, bear in mind, the last VAB end-to-end testing was on 11 August. So that time period, that 20-day period, actually ended on the 31st of August. but NASA got a 5-day waiver to that. It was good to the 5th of September, which just passed yesterday. Today is the 6th of September, in the wee hours thereof. So, so NASA's waiver would primarily, though, be contingent on some voltage testing of the FTS battery. So if the STS battery has the right voltage performances, they've got a better shot at getting these waivers from the FAA. That's not saying it's going to happen. That's just what the potentials are for that approval. Like I said, it's got to get approval from the range. And there's a couple of things they're looking at. Again, it's got to do with its cycle of test, and it's got to do with the very nature of the battery itself. And the battery will be the governing thing on that. Now, a lot of people have come out and says, oh my gosh, what are we doing? And why are they having all these problems? And it's got to do with the use of hydrogen fuel. The hydrogen fuel has to be cooled down to minus 423 degrees Fahrenheit. And that's pretty cold. You know, there was Saturn V F1 engine used liquid, and the fuel for it was actually, it had a LOX in it, but the liquid hydrogen, no, excuse me, it had liquid kerosene. The upper stage, the second and third stages, though, did have liquid hydrogen. Now, typically in rocket programs, liquid hydrogen has been used for the upper stages, and you just try to get a lot of thrust with the first stage to kick you into as much velocity as you could get early on. And sometimes that meant using denser fuels like kerosene, or in SpaceX chance they use liquid methane. So it's a big difference. Liquid methane is like maybe minus 116 degrees. So it's a lot easier to work with than that real cold liquid hydrogen. Liquid LOX is minus 200, I forget right off the top of my head. But anyway, it's not near as cold as liquid hydrogen, but colder than a liquid methane. But the thing about the hydrogen is the smallest molecule there is. And it's very leaky, even under any circumstances. Hydrogen is a very leaky gas. And so when you couple it with the fact that you have these cryo temperatures, it puts a lot of strain on the systems. And, you know, Shuttle had a program, had that summer in 1990, where all summer long they were chasing hydrogen leaks. It's just a tough gas to use. And but a lot of people said, well, Greg, why in the world would they use liquid hydrogen if it's a tough gas to use? Well, because it gives you high specific impulse when burned. It is the most efficient fuel in terms of specific impulse because it's a lighter, a lighter molecule, the H2, and it can be kicked out a lot faster. So it's that velocity that gives you the higher specific impulse. A specific impulse, one way to measure it, there's a couple ways to measure it, but the way it makes sense to the layman is it's pounds thrust per, pounds thrust per pound fuel burn. That's one quick and easy way. It's not miles per gallon in rocket jargon. So, and it's measured in seconds. So to give you an idea, the Space Shuttle main engine, or which we're using, which is also now known mainly, it's just we're not using the Space Shuttle by its older name or the other name for it, the RS-25 engine. The RS-25 engine produces 453 seconds of specific impulse at sea level. And as you get higher in altitude, that specific impulse increases. And if you have engines that are built for a higher altitude specifically, they can have bigger engine nozzles that can give them more area for the thrust to push against, which gives you even more specific impulse. So that number goes up with altitude, especially for engines designed for that, like upper stage engines, like the J2 engine, the RL10 engines, and the Raptor engines, for example. So you don't want to build an engine nozzle too big on the ground, and you get burn instabilities, but you want it big at altitude. And some RL10s actually had nozzle extensions to extend that nozzle to make it even more efficient at the higher altitude. So there's a lot of things like that come into play. But it had been the rule of thumb for a long time that the upper stages would use the hydrogen because of the efficiency up higher. So Greg, why in the world would we use it burning from the ground? Well, they started that with a space shuttle because it really was a all the way to orbit engine. And it was a case that it was, in a sense, the upper stage engine. The SRBs on the shuttle and now on Artemis are those big heavy thrust engines analogous to the F1 engine of the Saturn V. Now, to give you an example to compare it with, now there's two reasons that we use the hydrogen. One, it's highly efficient. The 453 seconds of impulse is the most efficient, rocket engine in the world, and it's pretty near the theoretical limit, which makes that engine kind of a Ferrari of an engine, especially when you're going to make it reusable. So we're going to be trying to go away from that with the RS-25, but it's still a difficult fuel to use. But the other aspect was Congress mandated, that NASA use the older engines and older technology. So it was kind of given to NASA to do that. They didn't have the choice. It was deemed that they wouldn't have to develop a new engine. It would save time, save money, not developing the engine, blah, 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 blah. And, when you look at the way government programs run, how they have to spread them out like peanut butter to get political support across the nation, that's understandable. But we're going to go into the politics in a future video. I've been promising this for a while, and I will still do. We're going to talk about politics real near soon of how this program evolved and how commercial space and these programs have come to us both today. And there was a lot of politics in that. So quite a lengthy discussion that I'm eminently qualified to talk about because I was chairman of the policy committee of the National Space Society for 10 years, and I played a role in that. And I got the article in this magazine that outlines that and how I went to Senator Nelson at a very key time. And I wrote this article about consolidation, or we'll talk about that later. So let's get on to this now. The Raptor engine, by comparison, has somewhere between, they usually rate it in a vacuum specific impulse about tops about 380 seconds, which is really good. That's really good for a specific impulse. It's not where the SSME RS-25 is, but at sea level they don't get that. So it's maybe 365 to 380. I'm not as familiar with that program, but the Raptor specific impulse is, like I said, it's about 365 to 380 seconds, depending on where in altitude you are. Okay, that said, by comparison, the shuttle SRBs, they provide they were 3.3 million pounds of thrust each. On the Artemis, there'd be 3.6 million pounds each because they've got an extra fill segment. They burn a little bit longer. You give something like 25% more total impulse than the old shuttle SRB. So it's a more powerful engine. So that's what makes the Artemis, when it launches, will be the most powerful rocket engine or rocket launch to date. Now, that said, the SRBs had a specific impulse at sea level of 242 seconds, nowhere near what the SSME or the Raptor engines have. But by comparison, the Apollo Saturn V F1 engine had something on the order of 264 seconds, of 264.72. Okay, 264.72 seconds specific impulse at sea level. That would also go higher as it got toward the end of its burn. And it burned for like 159 seconds. The old shuttle SRBs burned for 120 seconds, and the Artemis will burn a little bit longer. I don't remember the exact number of seconds on that, but anyway, so that's what we're talking about. There's a big difference in these engines. They have each has their own advantages, but then again, for the Raptor engines, their primary advantage is they get to operate in a lot more normal temperature range. The gas methane is not as leaky, and because you're not at really cold temperatures, you don't have as much problem with things like quick disconnects. You got to remember, a rocket's got all this plumbing to feed to the rocket, then there's plumbing to feed up into the fuel tanks, and then there's plumbing to go down the fuel tanks and down in the engine. There's plumbing around the engine for how you cool down the engine nozzle, how you preheat the fuels, and how it goes through the thermal pumps. And it all depends on the engine cycles that you use as to how that plumbing is arranged. We will talk about that in a future rocket engine video. I'll probably do a Rockets 101 class, which is going to be really simple for the layman, and then I will graduate to more advanced rocket engine talks later down the road. So subscribe to my channel, bang the notification bell, and click off, because I got more to bring you on these topics. Now, that's the kind of stuff we're coming up with. So why, what happened with the Scrub, and for those that haven't tuned in on it, we're going to go to SpaceX next. What happened with the Scrub is that the quick disconnect that went into the tank, they say, with the fuel system, you have to have a fuel line that can break away quickly so the rocket can launch. And that's why they use the quick disconnects. You have them on quick disconnects for electrical connectors. Everything that connects the rocket has to be on a quick disconnect. That's something that can seat, seal, and break away. Now they have to use seals, and you can't really use a metal seal, even at those temperatures, because it's got to be a seal that's malleable, very malleable, that will completely stop up, cracks and any oddball things about the interface, that will seat properly. Well, rubber, just if you remember the old space shuttle accident, the Challenger accident, they just, Feynman, was telling NASA, dipping the O-ring samples in this water glass with ice in it, and he was testing and finding he couldn't squeeze it near as much after he dipped it in water ice. That stuff, rubber, and most of the synthetic rubbers really aren't that good when you get down to just a regular freezing point. The regular freezing point is 0 degrees centigrade, 32 degrees Fahrenheit. Imagine going down to minus 423 degrees Fahrenheit. That is extremely cold, and it's extremely hard to come up with a good material that works and does that kind of stuff. Now they've done it, but it is a challenge, and has always been a challenge. And with liquid hydrogen, always will be a challenge. So that is part of what they're dealing with. And, but we've done engines similar to this for upper stages since been developed in the late 50s, and first flown in 1962 with RL-10 on the Centaur upper stage. And on the Apollo program, the Saturn V had J2 engines on its upper stages. It had 5 of them on the S2 second stage, and it had 1 of them on the S4B third stage. Greg, why was the third stage S4B? Because it was intended to be the 4th stage of a bigger rocket called the Nozzle rocket, back when they were going to do linear direct. But when they come up with linear orbit rendezvous, they were able to scale down and build a smaller Saturn V than the big Nova that they were looking to build. All right, all that said, so we've got a history with liquid hydrogen. It's highly efficient. It is the highest specific impulse, and a lot of people would argue that was the best to use. I had a mentor who was very much involved in the development of the F1 engine and the Saturn V program. My main mentor when I was a young engineer, he was a fan of density impulse as opposed to specific impulse. He thought density impulse would save better because although at liquid temperatures you can put a lot of hydrogen fuel in a fuel tank, it still took a really big tank, a really large structure, give you a little more air resistance, but mainly the structure had weight. You could, if you had a denser fuel, you could have a smaller tankage. And with that, you did have certain efficiencies that he thought outweighed the gain in specific impulse. And that's especially arguable on a lower stage vehicle. And that's why it was preferred to give you a real high thrust engine that maybe not as good in specific impulse for the lower stages. So, but most of the propulsion engineers I knew argued against that. Oh, they vehemently said you really needed to use a liquid hydrogen. Well, SpaceX seems to be proving that's not the case. So let's hope that that bears out and that they make all that work. But they got their challenges, and we'll get to that in a moment. But again, going back to the scrub, we had 2 launch attempts. The first one, that quick disconnect had a slight little leak, but it wasn't that bad. It was manageable. But this last time it was like 4% or something like that. It was a real high leak rate, which could cause flammability at the pad, and it was unacceptable. They could not load at the high rate. You just couldn't load that tank fast enough because it was leaking too much. It would not have been safe. They just could not proceed to do that. The first test, as you remember, the first scrub was because they failed to get a validated cool down of engine number 3. And that could have been due to the way it was actually plumbed different, that engine was. So they were going to try to bleed it down earlier, or did the bleed operation to cool and condition that engine earlier this time, but they never got to that because of the issues with the leak of the hydrogen at the quick disconnect in this case. So they tried several times. We tried several times to get that to work, because sometimes you can get those to seat by just changing the temperatures. They cooled it down. I mean, they allowed it to heat up, and then they hit it with the fuel again to cool it down, and vice versa. And they tried fuel pressure. So they tried pressure. They tried temperature cycling. They even thought about trying to put just a little bit of mechanical force on it, but they deemed that would not be very effective, and it was going to take a lot of time. So they ruled that out, and they did not go down that route, because right after the quick disconnect, there was only going to be able to apply 2 psi to it, and they did not think that would be enough to make a difference. Now, all that said, that's kind of what got us into the first scrub and the second scrub. But they really tried, but they ran out of time before, the launch window closed, and we just weren't going to be able to pull that off and get it fueled up in time. And you had to get it fueled in time and cool that engine number 3 down. So, and they didn't change out the sensor. And there was a case, where the sensor was bad or not, or whether it was the plumbing that caused a more resistive flow at the bleed operation. And I think they did. These are the same engines that were fired at Stennis Space Center, and they did a full duration burn. At full thrust, it worked just fine. So you have the full, they did a partial green run, and then they did a full green run with an 8-minute fire at Stennis. So they have the expectation that these engines should operate just fine. Like I said, they have been fired. So that's what we're going to try to do. It's the 3 options, and the one they're really aiming on for first is the one that hopefully, if the range will give them the waivers, if the testing works out with the batteries and everything in the flight termination system. Why the flight termination system? Because that's to protect public safety. If the vehicle should go awry, you don't want this big thing coming back in on populated centers when it's got the explosive, enough fuel in it to give you explosive fuel, like a small atom bomb. I've talked about this in some previous videos, and one of them I just said, hey, well, SpaceX nuked Boca Chica. And I know it made some people kind of unhappy. But the whole thing is that the Starship actually has twice as much fuel as the Saturn V or the Russian N1 rocket. The Russian N1 rocket blew up on both ascents, mainly because they had so many engines that were having problems with them. Not as many as SpaceX was carrying, though. But hopefully SpaceX is better at doing this than Russia was. But still, there's a challenge to that, too. But then again, and they had some acoustic problems with the N1 rocket. But the N1 rocket flung debris 6 miles. And Boca Chica was like 2 miles from the launch complex. I'm going, at the Cape, the NASA facilities or main facilities, like where the VAB and the mission control, the launch control center is 3 miles away. And that was considered to be quantity distance. Quantity distance is how far you expect debris to be flung and to still be safe. Yeah, 3 miles may be short, given all these things. But at least they're in buildings, and it's NASA property and civilian property that's not NASA is much further out. So, it made me wonder. And actually, one of the Starships did fling a little debris on upon explosion, about 6 miles. It's light debris, but some did go. But that was for the upper stage Starship. The whole stack has an enormous amount of fuel in it. But that said, let's hope SpaceX has got all that mastered and these things don't happen. But that's why you have a flight termination system, is to keep, and the mission of the 45th Space Group, whatever they call themselves now, still 45th something. I used to work with them back in the old Ares days. I went down and met with them several times back then. And, those guys, they'll work with you to a certain degree, but they got their requirements. AF Spec 910, I forget the exact name of the they got huge multi-volume specs that that you got to meet those specs, and their safety requirements are very stringent, and for good reason. They're protecting public safety. That's their job. That's their mission. You can't launch on the range until you assured them that you met their specifications. That's how we can still have, Titusville and Cocoa Beach and all these nice, wonderful places in Florida we enjoy. And safety for people. There's a lot of other things that have to be done too prior to launch, to notice the airmen, the seamen, and clearing out the immediate launch area. So that's a whole lot of stuff that they're involved in. I myself have used Eglin Air Force Base for range schedule servicing, so I know what that's like. And I've also filed launch waivers with the FAA. So I've been through that process for my own little rockets that I launched from balloons, believe it or not. So that said, Hannah dealt with the 45th Space Group back in the day, and around 2010. So I know what that's like. And prior, a few years prior, back in the old Ares days. So to get on with SpaceX here, so that is the options for the the Artemis program. And so the Artemis is intended to launch, and we got 3 options. And of course, if option 3 fails, we go back to either 1 or 2. So we'll see how that works out, and how that plays on the schedule. And hopefully that we'll get all this worked out, and we can pull a rabbit out of the hat and get this bird flying. You got to remember, those we've had on one occasion we had a shuttle flight delayed 20 times. I guess that was back in 90. During that summer, they were chasing hydrogen leaks. And even Bill Nelson's flight, the current administrator of NASA, when he was a congressman, he flew on a space shuttle. And that flight got delayed 5 times. So that's just part of the deal with dealing with liquid hydrogen. It's not very forgiving in terms of loading and leaking. It's problematic in that area. So maybe SpaceX, will usher in a new era with their methane fuels. And methane fuels burn cleaner than diesel fuel or kerosene or the rocket grade versions thereof. But it's probably not as clean as liquid hydrogen. Liquid hydrogen, when liquid hydrogen combusts with oxygen, the combustion product is water. When you combust hydrogen and oxygen, you get water. Electrolyze them, and you can break them apart, right? Anyway, so SpaceX. Well, now SpaceX is also trying to get up, and they've got their Booster 7 and Starship 24. And they got both prototypes in active testing phase, and they have been for about 4 months, beginning back in April to May timeframe. And now they got this new engine, the Raptor V2, similar like V2, because the new Starlink satellite's a V2. Yeah, and I knew guys who actually built the original V2 rocket. I knew a bunch of those guys when they were still alive. I knew some of them quite well. And but that's not what the Germans called it. That was the American name for it. The Germans called it the A4 rocket. Maybe you didn't know that. But in any event, so this new V2 Raptor can actually produce 25% more thrust than the older Raptor V1. So it's and it's got some new features to it. They've changed it where it has a modified way that engine operates, mainly with respect to the startup and shutdown operations to make it more efficient and safer, which is what they need. And since the middle of July, SpaceX has performed about 15 to 20 spin prime tests, where they spin the turbines up and everything, between the Ship 24 and Booster 7. And Booster 7, though, now it's going into the active firing phase. They're trying to test the engines, but they've only had, they've only had 3 static fires with Booster 7, and they had 1 with 1 engine. And so no, they did 2 with 1 engine, and they've done 1 with a maximum of 3 or 4 engines. So, and I think Starship 24 is conducted 1 static fire with 2 engines. So they're not fired the full complement of these engines yet, as yet. So there's a lot to be seen for that. Booster 7, hey, it could be several months before they get up to a full 33 engine static firing attempt. And you would think with less engines that the Starship 24 should be a lot more straightforward. But it appears that it's requiring about the same kind of effort as they're having to put into Booster 7. It's got its own challenges. And so they're working this out. So there's several months before they get all this stuff done. And of course, they still got to get an FAA launch approval. And I talked about that before, and I thought it was kind of, I can see a lot of why the FAA is putting a lot of pressure on them. But some of the stuff seems a little political, a little over the top. If they got to pay for some fisher things, some fisherman association things or something there. I mentioned before, there's 75 checklist items that SpaceX has got to do to satisfy the FAA. And some of them have nothing to do really. A lot of them are environmental, but some of them seem to be purely political. I don't know. That's not my wicked tea to cross all that political stuff on that, because that's their, I've done policy before for years, but politics is a strange fellow, and politics drives everything ultimately. All these things where you get approvals and the things that the government lets you do are politically driven, sadly to say. But there's some validity to that, especially with respect to ensuring public safety. Now, one of the key objectives of SpaceX is to ensure they're testing to try to ensure that if one of those 33 engines fail, it doesn't have failure propagation that affects the adjacent engines. So if one engine blows up, it don't take out the engine next. I have seen on a rocket where one engine blows up and then one next to it blows up instantaneously almost. I mean, just from human eye, it looks like it's instantaneous. It would be one engine causing the other engine to go. It happens really fast when it happens. So SpaceX is trying really hard to ensure that don't happen, which they need to do when they got up to 33 engines. Whew, that's a lot of engines. it makes me wonder, did somebody in the reliability department of SpaceX forget to give the note to Elon to say that reliability is inversely proportional to parts count? Hey, Elon, you might want a bigger engine. Hey, I don't know what all their trade space included, but typically in engineering organizations, we do a lot of trade studies as to optimize systems to figure out what's the best approach. You would use this many engines, that many engines. Back in the old days when we were still trying to come up with how we were going to go to the moon and Mars and these things, we were looking at many. We had hundreds of different rocket options. We were weighing many clean sheet designs, existing boosters, shuttle-derived variants. We were weighing a lot of things, but in the end, none of this analysis we were doing mattered because there was a dictate that you shall use these systems, and that was came down initially from NASA Administrator Michael Griffin, but he got kind of his program, the Constellation program, got shut down, and there's a whole politic about this. I'll discuss it later, how the Artemis SLS configuration came about and how we managed to maintain, also to have commercial space at the same time. So that's an interesting discussion in and of itself, but that's outside the topic of this video. So stay tuned for that. And I'll be talking more about, there's a lot of space happenings right now, lots going on. I was kind of beat after supporting 2 launch campaigns in a week, and I have some personal business I had to tend to, so that's why I'm a little bit slower coming in with this video. I didn't do an immediate post scrub video like I wanted to, but I do have new information that you haven't heard yet about the options we're weighing. Hopefully that's all brand new out here, and hopefully I'm one of the first to get this out. So guys, stay tuned. I got a lot to bring you. We got a lot to offer. Space is getting exciting. There's a lot of things coming down the road. And guys, we really got to do this because I will cover in the future what the challenges that China poses if they get to the moon first. I'm going to do a whole video on that, but I might do another on their capabilities. Like they're coming up with a 1 megawatt space reactor, which is 10 times more powerful than all the solar rays on the ISS. Holy smoke! What are the Chinese up to? The Long March 9, which would be more powerful than Starship, and they're working on a reusable Long March 9. I've covered that in a previous video. So my friends, subscribe to my channel, bang the up notification bell, and click all. Much more to come. I'm going to, with that, just say thank you so much for watching. I hope you're having fun. Space is going to be exciting. If we can stay out of WW3, let's pray that don't happen. If we can stay out of WW3, maybe we're going to have an exciting future here. Cross your fingers. Let's hope for the best. And with that, I want to say, Greg out.